I was showing a particular node and saying, well, the representation associated to this and the representation associated to that node and so on is the following. You all know, I hope, that I did say, that each node represents a simple root. Okay? And the linking diagram tells us how the simple roots are separated from each other, meaning the angles between the simple roots, and from them we could construct the whole root system. Now, we also said, I think, that we can describe representations by giving a point in what is called the weight lattice, which is the dual of the root lattice. So the root system produces the simple roots produce a lattice, right, in an r-dimensional space. And we also said that irreducible representations are classified by points in the dual lattice. Okay. Now, a very important role is played by representations whose vector, well, the vectors in the dual lattice are called weights, and they are denoted usually by mu. Okay, so these are r-dimensional vectors, and there is a very special role played by r of them. So there are r vectors, which are very special, and they define representations, and they are called fundamental weights, and they satisfy this relation. So if you see, they are dual to the simple roots. So that's why I can associate a given representation or a given fundamental representation to each one of the nodes in the linking diagram. So what I kept saying yesterday all the time was really referring to the fundamental weights that define representations associated to one of the nodes of the linking diagram. Okay? Very good. So whatever I did there, I told you this is something for you to play with, the example of SU4 cross, which is isomorphic to SO6, and then move on to study the representation theory of SO8. Okay? So that's an exercise for you. We did all that just in order to find out what the massless spectrum of this theory is. This is a massless sector. Okay? So what's the meaning of this plus and these minuses here? We have like 6 different kinds of pluses and minuses. So it's good to remind ourselves from time to time what they mean. So what do they mean by this plus here? Is what?
Chirality of the vacuum.
It's the chirality of the Raman vacuum. Because it's a spinor, right? It's a Weyl spinor. So we have 2 possible chiralities in SO8. And we have to tell which one we're choosing. Okay? So yesterday we said that from here, we get a spinor with plus chirality and a gravitino with plus chirality. Okay? From here we get another spinor with negative chirality and a gravitino with negative chirality. We said that these guys were called dilatinos or dilatini. And these 2 guys were called gravitini. Here we got something we call the dilaton, a 2 form, which is usually called the NS-NS2 form. And we got our metric, or what is going to play the role of the graviton. Okay, and it's going to produce and induce a metric. Once we consider coherent states of these guys, we'll produce curved spacetimes. Now this sector is the same on both, so I don't have to do much here. It's good that on both theories we have gravity. The difference here is that these 2 sectors are identical from the point of view of representation theory. They represent 2 dilatini and 2 gravitini with the same chirality. So this theory is said to be chiral. What did we find in the RR sector? Well, in this case, we said Well, let's see, which one we do first? Let's do this one. So we found a one form, right? We found a vector. And we also found a three form. So I apologize a little bit because I'm changing the notation. I think we call this differently, right? But let me just, I want now to, I'm going to try to unify the notation for all the differential forms that we found. So we found a one form and a three form. So I'm going to denote by an and m in space time. Okay? So this is a one form, this is a three form. Now you can complain and say, well, but this is a two form. Why don't you call it A? Yeah, in principle I should call it A, but I'm not going to be consistent. Okay? Sorry. So and here, what did we find? Well, we found a zero form. Well, a zero form is just a scalar, right? So I could also call this A0 NS NS, and this one A0 RR, but I'm not going to do that. I could do many things. Here we had a two form, which some people call this one actually B2 RR. Okay?
Wasn't the previous notation consistent?
What do you mean consistent?
I mean, it was consistent with itself, right?
Yes, but
now, so what's the point with changing to this?
You will see, trust me. This notation will be convenient for something we're going to do. It's not clear why I'm changing my notation, but... Okay, so we have this. Now the question is, what's the meaning of all these differential forms? That we get here and there. So what could they possibly mean? Now, here is important to recall what we discussed yesterday. We're not dealing with a string field theory for which I can just give you the action or whatever replaces the action in that case, and from there you can construct everything and derive everything just straightforwardly following some rules of which we still don't have. Okay? Instead, the only way we have of understanding this theory is building it piece by piece, painfully discovering pieces, putting them together, and then realizing that there are other pieces that we're missing, which we didn't think about, and we have to put them in. And once we put them in, we discover that there are new pieces we were missing, and keep going. Okay? If we had this ultimate description, which is just the analog of the quantum field theory for particle physics, then we wouldn't have to be doing all this. Everything would come in a single package. But we don't have it, so we have to discover it piece by piece. Okay? One of the first indications that we have to do things just like that is that quantizing the string tells us that there are these differential forms, but it doesn't tell us what they mean. So we will have to guess what they mean, and then go back and check that everything sounds consistent, and all the pieces fit nicely. Hint one for what these guys actually mean. Well, say in 4 dimensions, we have a one form and we know what it means. It means this is our gauge potential. And what it means is that if we have the wave function, this is a wave function of an electrically charged particle. This is just in quantum mechanics. And our charged particle moves in space-time. This is time, and this is space. Okay? And we have our particle that moves in space-time. Okay? From some point A to some point B, then the wave function changes in the presence of a background gauge potential. The wave function changes by a quantity which is A mu dx mu integrated over the path. And the strength is given by the electric charge of the particle. So that's how the wave function changes. But now we recognize this, we can write that as a coupling in the world line theory of this particle. So from the point of view of the world line, we can write this as A mu x prime d tau. Okay? So the presence of our gauge form potential somehow can be taken to tell us that there must be objects that couple to it which are electrically charged. Okay? Well, we also did another one. We also know another example. Say in 10 dimensions, we have our B field in the NS B field. And by now we know what this B field does. What we have is that in 10 dimensions, we have a string moving. Okay? And this B field couples to this object or to this string the way we discussed last week. Over the world volume. Or more explicitly, we can write it as we did last week. Okay? So this is our hint number 1. We know that in all the cases we have considered, every time we have a gauge potential, let it be a 1 form or a 2 form, it couples or it signals the existence of an object. In this case, is this string. Okay? Now, hint number 2. Oh, it's really unfortunate. Well, let's try. Hint 2. Let's go back to 4 dimensions and consider Maxwell's equations. In the vacuum, they tell us that this has to be 0 and this has to be 0. Okay? Those are really the field equations. If we are not in the vacuum, the only modification we made is introducing here a 3-form current, electric current. Some people like to think about this as a 1 form, but then you have to put the star, and we still have this thing equal to 0. Okay? And it's this equation precisely the one that tells us that F could be described as the D. It's this equation that tells us that F can be described as the D of a 1 form, as the stereo derivative of a 1 form. However, if you look at the equations in the vacuum, it seems that Maxwell's equations have an asymmetry. What is a symmetry in the vacuum? Well, you can exchange F and F star, and how would you know the difference? the equations are invariant under that transformation. Okay? You would say, well, who cares about that if we know that if we're not in the vacuum, we don't have that duality, right? Well, but in many theories that you can consider, you can discover that as solitonic solutions, the theories will have objects that have magnetic charge. So people have been led to consider that this duality might actually go through, even in the case where you have charges, and you could also have magnetic charges. Now, you might say that you lose this, right? But imagine that the magnetic charges, or this magnetic charge, or this magnetic monopole is just localized somewhere in space-time. Sorry, somewhere in space. It's actually moving in time. Then this equation will be true, not globally. Okay? So this is not going to be true globally, but it's true locally. Okay? So what do I mean by locally? You choose a region of your space-time which is contractible, meaning that it doesn't contain the charge, it's not enclosed there. And then on that region, F is equal to dA. Now in another region, F will also be equal to dA, but if you patch them together in such a way that you enclose a magnetic monopole, you should not find that the whole thing is described by the same A, by the same gauge potential. Somehow the gauge potentials in the different patches that you choose will have to differ slightly in order to allow for this magnetic monopole to be there. Okay? But that's not something we want to discuss. All we want to say is that in 4 dimensions, electromagnetic duality is hinting that if you have an electric charge, you could also have a magnetic charge. Okay? Now, there is something particular that happens in 4 dimensions. Here we said that associated, yeah, it's really unfortunate, the thing of the blackboard, because, well, let's continue hint 2 here. Hint 2, part 2.
Yes. Here, for example, for the electric current, shouldn't it have another star?
Yeah, I said it, but I probably said it too fast or too, or not loud enough. I said that some people like to think about the current as a 1 form, then you need a star. If you want to think about it as a 3 form current, you don't need the star. It's just as. So here is my definition of a 3 form current. But then some people might be Aitor, who likes to think about the form as a 1 form current. Then you need the star. Okay? Yeah, I knew that this wasn't going to save me any time. But I did it nevertheless. I mean, introducing just a 3 form and not the 1 form. Okay, part 2. So what are we learning here? We're learning that if we have an electric charge, right? We have an electric charge. This one couples to the gauge field, to the 1 form, associated to D, right? F is a 2 form, this is a 1 form. Now the magnetic charge what is this guy? Well, we just said that it's a particle. It's also a particle, right? So it also has to couple to a 1 form. But which 1 form? Well, it will have to couple to the 1 form of a field strength, which is the dual of the original one, meaning that this guy is star of the original one, right? And the gauge potential that we're going to introduce here is the D of this. Okay, so this guy couples to that. Very good. But this is a peculiarity of 4 dimensions, that somehow the electric charge and the magnetic charge are both particles. And why is that? Let's try to generalize this to more dimensions. Okay? So let's rewrite this. So let's do electromagnetic duality in d dimensions. Okay? So what is it going to change? Well, the electric charge is still an electric charge, so this is still true. Okay? So the electric charge is a point here. We don't want to change that for the moment. But how about the magnetic charge object? What is it going to be? Well, we can keep exactly the same definitions here, but we have to change the kind of forms they are, right? Because if we just keep this everywhere as an equation, the star of a two form in d dimensions is not a two form. Now remember what the star means, the Hodge dual. Of course, it depends on the signature and so on, but the way you construct it is by putting the epsilon tensor, which has d indices, and you contract it with the original form. The original form in this case has two indices, is a two form, right? So our new object here has the remaining indices, so from 3 to md. So what is this? This is not a two form. It turns out to be a d minus 2 form. And if our field strength is a d minus 2 form, the gauge potential will be a d minus 3 form. Okay? So here is a surprise. If we try to do just the same electromagnetic duality, but in higher dimensions, we will find higher dimensional objects. Because from this point of view, we know that if we want to couple this to anything, whatever we want to couple it to will have to have d minus 3 dimensions, right? Just like this one has 1 dimension, this one has to be something that has as a work volume d minus 3 dimensions. Otherwise, we won't be able to couple it. Okay? Very good. So what would be the coupling? So the conclusion of hint 1 and hint 2 is that objects with higher dimensions exist, or they must exist, from the mathematical structure of this. And every time you see a differential form or a gauge potential that has some number of indices, whatever the object it couples to will also have that many dimensions. Okay? So, in general, let's say that you have a gauge potential, which is a 1 plus p form. Okay? Why am I separating the number of dimensions as 1 plus p? The reason is that I'm thinking about this one as being time. And everything that we're dealing with will have time, right? So it's boring to keep track of that index. So somehow it's better to talk about the objects by the dimensionality of the space directions. Okay? So we're just going to keep track of p. Of course, in the computations, we will keep the 1. But when we are referring to these objects, we're going to talk about this object by p. So this gauge potential will couple to something that has as work volume a p plus 1 dimensional submanifold of our space-time. Okay? So the object this thing couples to, So we have our space-time again. We now have a big object which has dimensions 1 plus p dimensional. Okay. So we're going to refer to this object as a generalization of a membrane, and somebody came up with a name and decided to call these things p-branes. Okay. So that would be the object that couples to this form. Okay. But something else we learned from this description is that if you have an object that couples to some form, you should also have the magnetic dual. So can anyone tell me what the magnetic dual would be of a p form in p dimensions? All you have to do is to follow this line of thought, replacing this by a p form, by a 1 plus p form. So what's so you already did?
Minus p plus 1. Minus
P minus P minus 3.
Where do we do it? Just 1 second. Oh no, I don't want to. Sorry, we cannot continue with the class. With the lecture. Oh, very good. Brilliant. That one. We will also use it. Don't worry. Well, here we just want to say, I just want to write the conclusion of that, or do the computation. So if we have a p-brane, it couples to a 1 plus p form, right? And then somebody who wants to tell me what the magnetic dual is going to be. It's a D, I heard D minus something.
minus p.
D minus P.
Only the spatial part would be minus 4.
Yeah, remember the notation is that the P brane, the P only refers to the special. So this is your proposal. So let's just do it quickly. So this guy will have a field strength which is P plus 2. It will be a P plus 2 form. The dual will be the star of this guy, which would be a D minus P plus 2 form. But we are not interested in the field strength. We want the gauge potential. So the gauge potential will be a D minus P plus 3 form, well, or D minus P plus 3 form. But remember that or I should write this as D minus P plus 3, P plus 4, plus 1. And this will be our P star, or P dual. So this is the dual, the magnetic dual.
Why would it include the time dimension?
Why not?
Because
everything has time. Sorry?
Because in the original form you have the time dimension, but after you take the Hodge dual.
Yeah, so here it is. This is time.
I mean, after you take the Hodge dual, you are going to the other part of the dimensions, which are purely spatial. And then you obtain the original.
Right, so we can think that we're doing this, say in Euclidean space and then going back. But the physical objects, whatever the physical object is, must have a time direction. Otherwise, it will not be physical.
No, I mean,
No. So, sorry. No. Sorry. I misunderstood what you were asking. Are you asking in the definition of the dual, if we are taking these ones through these, are not the indices of, yeah, I understand what you're saying. So I think remember, these guys, each index here goes from 0 to D. We're not choosing particular components, right? Was that the question? Yeah, I think.
More or less.
Yeah. We're not choosing particular components here. We're contracting it with the full tensor, so the remaining object will have all components. Yes.
But, I mean, for example, in electromagnetism for dimensions, if your electric potential is dt, and it's proportional to dt times some function of r, like in say raised to Armstrong, then when you take the two form, that's dr and wave dt. And the dual to that is
Well, you have to be careful because sometimes you will get 0, right? Depending on you will not get something trivial for this guy if you don't have a magnetic charge in the story, right? So you'll have to consider black holes with
So Ryzen at Dionic.
Ryzen and Nostrum only has electric charges, right?
Yes, so Dionic Ryzen and Nostrum.
Oh, you want to consider Dionic? Okay.
But that doesn't. So the
Do you know the solution?
yes.
How many supersymmetries?
Oh, I don't know how it looks in terms of symmetry, but I can write down the metric.
Without supersymmetries. You know what it is?
I mean, you just
In what theory does it live?
Electric, magnetic, you got it.
Yeah, well, let's not get into. Let's discuss. Well, you can show us the solution after the lecture if you want. Okay. Okay. Very good. Right. So now we have these objects. If we go to 10 dimensions,
Sorry,
yes.
why we just call the A's as branes or P branes? I mean, we could just call F's as P branes or P plus one.
Yeah, that's just convention, right? We can call things.
Right, but then the dual of some P brane, I mean, in general. Is
Oh, you
not
mean
P-
why doesn't the object couple to the field strength?
Yeah.
Is that what you're asking?
Um,
No. What is
that's
it that
not
you're
that.
asking?
But when we talk about the dual of some P brane itself or whatever, we should first think about it. What is it, and then look at it. Because, I mean, if we just talked about the dual of F's, then it wouldn't be. I mean, we couldn't use that formula for that, right?
If we just use the dual of F, sorry?
Well, if we have an F, which is a P brane, then is it possible to have?
No, these are forms, right? There are no p-branes in the F is a differential form.
Right.
It's the field strength of a gauge potential, and the gauge potential couples to the p-brane. So where in the story do you want to put your comment? So there is a p-brane that couples to a gauge potential. The gauge potential has a field strength. We dualize the field strength to go to the magnetic dual. So where in the line you're asking your question?
Well, I'm asking like. So what are the branes themselves? They should be some special things.
They are the generalization of particles, just like our string, right?
Right.
And they couple to the corresponding generalization of the gauge potential. Okay.
Ready?
Yes.
Why did you say it was gauge potential, not field strength?
Oh, the reason is that this guy. Remember, from the structure that we consider the way we discovered these guys were as representations of the massless little group, right? So we discovered that they were forms. If we want to describe them in space-time using a Lorentz invariant description, we have to describe them as forms. But remember that they are really massless particles, right? So we will have tons of extra degrees of freedom if we describe them in a manifestly Lorentz invariant way, right? And in order to get rid of those degrees of freedom, we need a gauge redundancy, right? So they are really gauge potentials. So the A's here, that's why I decided to call them A's all over the place, because they are really gauge potentials. That's the only way, introducing a gauge redundancy is the only way to keep the degrees of freedom that we see manifestly in the little group or in the Lycon quantization that we use, right? So the only consistent way with Lorentz invariant to describe these guys as forms in space-time is to interpret them as gauge potentials. And we know for a variety of reasons that the objects that couple to the fields, to some particular electric field or magnetic field, the way it has to couple is through, at least in a local way, is through the gauge potential associated to that object, not to the field strength, right? Now, that's a very good question. Why am I calling these guys gauge potentials? Or why do I think that they are gauge potentials? And it comes from the representation theory, from the fact that they are massless. If we didn't care about Lorentz invariance, or a manifestly Lorentz invariant description in space-time, and you never wanted to write an action, you would never talk about gauge invariance. Okay? If you were only interested in scattering states, you wouldn't even have to introduce Lorentz invariance in the first, gauge invariance in the first place. Okay, so now let's take what we discovered there and apply it to the guys we have here. So I'm going to erase this. We're not going to worry about the fermions. We're only going to look at these guys. So in the Ramon-Ramon sector, we have a one-form gauge potential, which by our study here, or by the hints, our conclusion is that this guy has to couple to what kind of brane?
Zero.
It's a zero brane. So we can now erase this. What would be the dual object? The magnetic dual object. Very good. 6 brane. And the reason you know is a 6 brane because we have to use D equals 10 in that formula. And if we use D equals 10, we get that this is a 6 minus P brane, the magnetic dual. So we have an A3, and this guy gives rise to a 2 brane, and its magnetic dual will have to be a 4 brane. Okay? Now in the NS sector, we have our NS 2 brane, 2 form, which couples to a 1 brane. But who is this 1 brane? This 1 brane is our good old string. So this is something that people call the fundamental string. And the reason they call it fundamental is because that's the basic object we started the whole story with. Okay? And the magnetic dual of this guy happens to be a 5 brane. And people call it the NS 5 brane. Okay? This is just so that when you hear in seminars something, you know what they are referring to. How about here? Once again, let's get rid of the fermions. Let's only concentrate on this guy. So we have this A0. What could that be?
Minus 1 brane.
Yeah, it looks like a minus 1 brane. That sounds crazy, right? Minus 1 brane means that something is even localized in time, right? So this only exists in the Euclidean theory and is an instanton. Nevertheless, we can compute its magnetic dual, and it gives us 7 brane. Okay. Our friend here gives us a 1 brane. And you see the reason for introducing the name fundamental string here, because now in type 2b, we're going to have another 1 brane. X dual will be a 5 brane. So we got a copy of this. So these guys, as I said, are often referred as NS for the corresponding brane, NS5 brane or NS1 brane. This one is usually called a fundamental string. This one couples to a 3 brane, and its dual is the same, it's a 3 brane. Okay? So do you notice any? Yes.
Why one of them is fundamental and the other one? Why call it like this?
Well, the deep reason why this one is called fundamental is that it's the one that appears in the perturbative description of the theory. The other one is a non-perturbative state. Okay? However, if we have in a theory something that relates the strong coupling and the weak coupling, sometimes the roles of each one of them can swap. Right? And you're doing something in your homework showing that type 2B does something interesting, right? Or I hope you are actually doing something in for your homework too. You know, the one that we gave you on Monday? That has a type 2B supergravity problem. Oh, but we said that you should do it before tomorrow, not today. So that's okay. I mean, it was recommended that you could do it, that you should do it before tomorrow.
It's better to do.
All right. So what's the summary here? So we got for type 2A, the kind of branes we got are 0, 2, 4, and 6. And for type 2B, we got -1, 3, 5, and 7. Well, you may ask, it seems as if something is missing here, right? We're working in 10 dimensions, so why are we missing here an 8? And here, why are we missing 9? Okay? Yes?
We're also missing 1.
Well, that's because I didn't put it. There is no interesting reason why we're missing 1. Yeah, that puzzle has a very simple explanation. Very good. So, this is a puzzle, and it's a puzzle that led to interesting discoveries. But I'll leave you with that question at this point. You might be able to figure it out, actually. What happens to these guys after we discuss what we're going to do next? Okay? But even before worrying about this puzzle, okay, why don't we see an A brane and an I brane here? There is even a deeper puzzle with this whole picture. It's a big puzzle. Okay? By the way, we should give a name to these guys to distinguish them from the NS branes. So we can call them RP branes. Right? R because they come from the Ramon sector. The other ones are called NS branes, so we can call these ones RP branes. Of course, both of these theories contain the same NS branes, right? Because they only differ in the R sector, so they should have the same kind of NS branes. So everything I said here is about the RP branes. So what's the big puzzle? The big puzzle comes from one of your tutorials. Was a tutorial or a homework? I think it was a tutorial, the one on T-duality. Was tutorial, right? Okay. So the puzzle comes from a tutorial. And it comes from the concept of T-duality. So you discovered that if you take the bosonic string, that's what you did in your tutorial, but say we do it for these supersymmetric theories. So take type 2A on R1, A cross S1. Okay, so we compactify on a circle of radius R. From your tutorial, you realize that there must be another theory that can be obtained from this if we apply this strange transformation called T-duality. And what did T-duality do? Well, it took one of the two sectors. Let me see what my convention is for that. Could be the right movers or the left movers. The right movers. Take the right movers. Let's call this coordinate is coordinate 9. Okay, it's the 9th coordinate, the one we're compactifying on a circle. So let's take this guy. And T-duality was a transformation that could be obtained by sending this to what? We keep the left movers intact, and what do we do to the right movers?
To minus.
Yeah, we send them to minus. Now, you did it in the bosonic string, but if you were doing this in the fermionic string, if you have worldsheet supersymmetry, you should do the same thing to the fermions in the 9th direction. So you should send these guys to minus themselves, right? But now when you quantize this in the Ramon sector, you should do the same thing to all the oscillators. But one of the oscillators happens to be so if you do it to those guys in the Ramon sector, you also have to flip the sign of all the oscillators. In particular, we have to flip the sign of D0 in the 9th direction. We'll go to minus D0 in the 9th direction. Okay. But D0 was proportional to the 9th gamma matrix in 10 dimensions. So we're sending this guy to be minus gamma 9. And if we do that, what happens to gamma 11? Gamma 11, being the product of all these guys, will then go into minus gamma 11. But what happens if we flip the sign of gamma 11? What happens to the chirality of the objects? It will swap, right? It will flip. So, but we're doing this only to the left sector, not to the right sector, right? So we're doing this, we're flipping for T-duality. Flips the chirality of the Ramon ground state in the right sector. Yes?
Do you only do that transformation for one of the chirality components and not for the whole?
Well, if you did it for both, you wouldn't change much, right?
Yeah.
But in your homework or in your tutorial, you realize that this duality that precisely exchanges, well, the duality that, sorry.
I mean for the fermion. You took the whole fermion to minus.
Yes, yes. The full superpartner of this guy. This is a Dirac spinor, right? So the dual of the boson on the world sheet was the Dirac spinor, right? You're asking if I have to put pluses or minuses here. Now, I'm taking this to be the Dirac spinor, the full guy, the full Majorana Dirac spinor. Yes.
Here when we change this minus sign, don't we change the sign of the boundary condition? And when we change the sign of the boundary condition, we go from one sector to an S sector.
No, I'm changing the sign of the full object, right? So everywhere, the same sign will change. Remember, the sign that you're talking about was a sign relative of psi plus and psi minus. That's related to the question, to the previous question. Am I changing both psi plus and psi minus? And the answer is yes. I'm changing the full Dirac Majorana, well, the full Majorana spinor, right? Very good, very good. Okay. But then what's the puzzle? I mean, I told you there was going to be a big puzzle. Well, first of all, T-duality is not just this, right? What T-duality does is to give you a new theory, but whatever new theory you're going to have is going to be compactified on a circle of radius what? So the new theory,
1/4 pi over r.
1 over r. So our new theory, whatever it is, the new theory is obtained from type 2A by flipping the chirality of the Ramon ground state in the R sector, okay, and compactifying the theory on R1,8 cross S1 with radius 1 over R. How is this statement meaningful in dimension-wise?
We also have alpha prime.
Yes, which I'm setting to 1. Just checking. Okay, so this should be our new theory. Whatever it is compactified in this way. What theory it is? Well, we're taking type 2A, and we're flipping the chirality of one of the Ramon ground states, not the other. So type 2A started as a theory that had different chiralities for both Ramon states. And now we're flipping one, and therefore we're getting a theory that has the same chirality on both states, on both ground states. But that theory, we know what it is. It's type 2B. So the new theory is nothing but type 2B compactified on this space. Why is that a puzzle? Well, the puzzle is that if you take R going to 0, right, we are supposed to get, this implies that we should get type 2B on R1,9. But we're supposed to get the full theory, type 2B on R1,9. But this theory has Ramon p-branes that are odd, and type 2A has Ramon p-branes that are even. That sounds like a puzzle. How are we supposed to start with a theory that has R p-branes which are even, and all of a sudden produce a theory that has R p-branes which are odd? Well, once again, every time there is a puzzle, either your theory will just collapse and it will be inconsistent, or you will discover something new about your theory. Luckily, in this case, you discover something new, and here is a hint. The hint for the resolution of the puzzle is the following. If you remember, in the second lecture, or maybe the third lecture, we discussed all possible boundary conditions for open strings. And we found that there were Neumann and Dirichlet boundary conditions. Some of you even did exercises, right, on the blackboards. What were you doing on the blackboards? Well, we said that people were only considering Neumann boundary conditions in space-time because otherwise you would have a theory that somehow breaks Lorentz invariant in the full space-time. Okay? But just for fun, we decided to see what would a string look like if it was living in space and it had some Dirichlet boundary conditions. So one example we did, maybe, I don't quite remember, but one example we could have done if we didn't do it, now in 10 dimensions, is something of this form. So I'm going to put an X if we have Neumann boundary conditions. And I'm going to put nothing if we have Dirichlet. Okay? Now you can tell how many more Dirichlet than Neumann boundary conditions I'm going to have, right? I'm going to have more of Dirichlet. So I'm going to put Neumann boundary conditions here, here, and here. And the picture for that maybe one of you did, if I remember, was something where we have time. Actually, we didn't draw time when we did that, right? So, well, let's not do it now. So let's put, we have x1 let's put x9 here and x2 here, okay? So I'm assuming that both ends of the string have the same boundary conditions, okay? So this is an open string. Both ends of the string have this set of boundary conditions. So how would the string look like? Well, the string is, I'm not drawing these directions, but it has Dirichlet boundary conditions in all these directions, so it's localized in all these directions, the endpoints of the string. The only one that I'm seeing is x2, and the fact that it has Neumann boundary conditions here and here, it means that it can move freely in the x1 and the x9 direction. So if x2 equal to 0 was the condition that I'm imposing as a Dirichlet boundary condition, it would mean that the end of the strings with those conditions would be forced to move on these planes, on this plane, but the string itself can do whatever it wants. Okay? So that's one of the exercises we did. Okay, that's pretty good.
Sorry.
Yes.
Why should both ends be on the same plane?
Because I'm saying that. Yes. So I'm declaring that I'm only interested in strings with this boundary condition for both ends. Yeah, probably you were one of the people who did an exercise where both of them had different boundary conditions. So yes, that's possible. Okay, but in your tutorial, you also study what happened to the boundary conditions when you compactify a direction, right? So imagine that we compactify, well, x9, as we're doing here. So we compactify x9. So let me draw x9 as a compact direction. So this would be x9. It has some radius r. And I'm going to draw x1. And that's it, because any other direction that I want to draw will require 4 dimensions. So this is x1, and this is x9. Okay? So if I do that, my string has endpoints which are free to move anywhere along the cylinder. And the rest of the string can do anything it likes. But in your tutorial, you found that under T-duality, we end up with a compact direction that has radius 1 over r, right? So this is x9. The x9 direction is a circle. And what happens under T-duality? What happens to the boundary conditions? So we had Dirichlet boundary conditions. Sorry, we had Neumann boundary conditions for x9, which is the one we're compactifying. Now we're doing T-duality on x9, and we find Dirichlet. So our endpoints that were happy to do anything they liked on the x9, x1 cylinder are now locked to some x9 direction, to some x9 point. So our endpoints of the string are only free to move in the x1 direction, but not along x9, because they now have Dirichlet boundary conditions. Of course, the rest of the string is free to do whatever it likes. So if we want to draw the new object under T-duality, so under T-duality, the new object would look like just like this. This guy got the T-dual version of an X is nothing here. And this is something that we could call a two-brane, right? The object to which these open strings couple could have been called a two-brane. Under T-duality, that guy goes into a one-brane. But isn't that exciting? It sounds precisely like the thing we needed to solve the puzzle. The puzzle was, how on earth can we produce odd-dimensional branes from a bunch of even-dimensional branes? So it seems that if our R branes, RP branes, are these strange objects on which the open strings can end on, then they will behave as the duality is telling us they should behave. Okay? So that was one of the first hints that these RP branes were actually things where these open strings could end on. And that's the reason why people decided to call them not RP branes, but D branes. So where did they disappear? Yeah, probably they disappear from the, yeah, that was probably on this blackboard, okay? So let's see that working in detail, or a little bit more in detail. So we start with type 2A, and we started with a two-brane, which now we're going to call a D2-brane. Okay? I'm not going to call them anymore R-branes, because now we just found that the consistency under T-duality suggests that they have to be associated to these D objects that we found at the beginning of the class, of the course. Now, if you have this D2 brane, and the 2 brane happens to have a Neumann boundary, produce Neumann boundary conditions here, or in other words, the D2 brane doesn't wrap the compact direction. Sorry, in this case, it wraps the compact direction. Under T-duality, it loses this direction. So if we have the D2 brane, two things can happen. This is a case we consider. The 2 brane wraps the S1 under T-duality, and then it goes into a D1 brane. Okay? Now imagine that we're considering the case of a D2 brane that doesn't wrap the compact direction. Okay? That's another possibility. Under T-duality, what's going to happen is that this Dirichlet boundary condition will go into a Neumann boundary condition. So our D2 brane will go, of course, nothing happens to this one. This one stays the same. All the action is happening here on the 9th direction. So this goes into a D3 brane. Okay? So I encourage you to keep playing with this thing. Take everything that you see on type 2A and compactify and see how they go into something else on type 2B. So this is on type 2A. This is a case of the D2 brane and how it goes into type 2B. Yes?
The next brains, don't they change? Is it immediate to see that they don't change? Or?
Yeah, that would take some time to explain. Yes, but that sector will basically stay the same. Yeah, maybe tomorrow we'll have time to discuss that, and probably we will, because tomorrow, well, depending on what we end up doing today. We will see. Yeah, we will see. Okay, so I want to finish just in 2 minutes. Let's see. What do I want to do now? So the last thing that I want to say is that once people discover that there are D branes, many interesting possibilities open it up. One of them was the possibility of finding interesting gauge groups in type 2A and type 2B. Remember, in type 2A and type 2B, we didn't have any SU3, and we want an SU3 for the standard model. How are we going to get SU3? And the other incredible development that happened was the discovery of the ADS-CFT dualities. Okay? So this, the second one, is something that you will discuss just in a course devoted to that, basically. So maybe we should concentrate a little bit on this, the appearance of non-trivial gauge groups. And all I want to say about that, really, can be summarized in a picture. So, let's see, is there something? So there is only one picture that I want to draw that will summarize what happens. So if you were to choose any of these branes as something where you want to live on, I mean, as a human being, you want to live there, which one would you choose? Well, you would probably want to choose something that preserves the dimensionality of space-time that you see. So you want something that has 3+1 dimensions. And what would that be? It would be a D3 brane, right? Just for that only purpose, for only that reason, I'm going to talk about D3 branes. And I'm going to ask, what happens if I have a D3 brane here? Okay, that means that I have open strings. And I have another D3 brane parallel to this one and separated by a distance L. This other D3 brane will also have strings that can go like this. But remember, string theory is made out of pieces, different sectors and different pieces that we put together and ask if they interact consistently. So just like these sectors are there, they would also be, to make happy a Lie, guys that can end on different D branes. Okay? Now these strings have some orientation, and that's something that we discussed a little bit at the beginning of the lectures. And that's how we said that these guys, from the point of view of the D brane, they look like electric charges with plus or minus. And this one will be plus and minus here. But plus or minus with respect to what? We said that there had to be, on the work volume of the D brane, somewhere there. This is, after all, this is a 3 + 1 dimensional field theory. So there are many fields that could be living here. The question is what kind of fields we have to introduce in order for this to be consistent. And one of them is a U1 gauge field living here. And there is another U1 gauge field living here. Now what we find is that we have two U1 gauge fields. And from the point of view of somebody living here, these particles look like massive particles, but they carry a vector index. So these are massive gauge bosons. I mean, that's massive vector bosons. Have you ever seen, or have you ever seen in any course, a massive vector boson? W. So from the point of view of these guys, this guy and this guy look like a W plus and a W minus.
But don't they transform in some kind of big pi fundamental?
Well, that's because you also have this other U1. But if you're living here, that's what they look like from the point of view of this sector. Okay?
But will they transform in that joint?
Very good. So the difference here, you would say, well, the signal or the appearance of massive vector bosons might be telling us that there was an enhanced or a larger gauge symmetry that was broken. Okay? The way it's broken here is not by having a Higgs in the fundamental representation, but by having a field that is in the adjoint representation. Okay? So how would you make these guys massless? Or how would you make these guys have a massless object as the lowest lying level in the spectrum of this sector? Well, these ones do, right? The question is, could these ones have as the lowest lying state in the spectrum something that is massless? Well, certainly not if this distance is not 0, because there is some tension and these guys will necessarily have some mass gap. Okay? But if we take L to 0, these guys will also have something massless in their spectrum, and that massless guys will be these guys. Then the question is, once L goes to 0, these guys, what do they do? And what happens to this gauge group? Well, the answer is that this gauge group, once this happens, gets enhanced into a U2. And these W bosons actually became the gauge bosons that you were missing in order to produce U2. Now, when you go from here to here, you're going into something that is called the Coulomb branch, because you're giving expectation value not to something that is in the fundamental, as we do in the standard model. That would be the Higgs branch. So separating these two guys is a different way that you haven't seen in your courses of breaking symmetry. Okay? And that's why we keep two U1s when you break U2 in that form.
Okay? Well, you see that if you keep only this guy, you see that the strings somehow fall naturally, or from the point of view of a subgroup here, an SU2 subgroup, you can think about these strings living here on this side as being the Cartan elements of the algebra. And the strings that go from one direction or the other can be thought of as the roots of the system, or giving you the roots of the system. Now, the guys going in one direction could be the positive roots, and the one going in the opposite direction could be the negative roots. Now, is that something that I just made up? Maybe. But let's see, well, you can start with things that you just make up as you go, and see if they make sense. Why not put another one? And in fact, put many, many of them. So let's put n d-branes together. So you have the first, the second, the third, and the nth one. Now you have the strings that go from here to here, from here to the next one. So there will be the next one here, and here. Once again, these individual ones that you have here look again like if they were the positive and negative roots of the system. Moreover, if you only chose the ones, well, the set of all positive roots will be obtained, or will look like we could obtain them, by considering guys that go from here to here, or guys that go from here to the next one, or guys that go from here to the fourth and to the last one. So all possible combinations of guys going from one to the other and from here to there in that direction could be all the positive roots. The ones coming back could be all the negative roots. And guess what? The ones that only go from one to the next one, what would they be?
Simple.
The simple roots. Right. So this little game tells us that this picture starts to look like what? Starts to look like a Wordinkin diagram. Okay? Well, this is a picture that can actually be made precise, and it turns out to work exactly as I said. I just said it like that because sometimes you just play around and say, well, what if this thing that looks like that was exactly that? And in this case, it turns out to be true. So n d-branes that are parallel to each other, if you connect them, if you put them on top of each other, you will have a UN gauge group.
A question on that.
Yes.
I mean, if you perform that limit L goes to 0,
yes,
you have basically just one brane with one concrete boundary condition for your strings. So what is the difference doing that with 2 branes or n branes? Is it just that you choose a priori some indices for your strings, string 1 going from brane 1 to brane 3 and so on, so that you just...
Excellent. If you had had that question, I don't know, maybe 15 years ago, so what's your name? I forgot your name.
Lucas.
Okay. They wouldn't be called Champaton factors. They would be called Lucas factors. All right. So exactly that question was asked. And precisely those indices at the end of the string are called Champaton factors. So people ask, well, what if you attach new degrees of freedom to the end of the strings? Can you build a string theory that is consistent? What would be the consistency conditions for those labels that you put in there? And the consistency conditions are precisely that they have to combine and interact as if they were precisely elements of a root system. That was in fact discovered before d-branes. Okay? So people had the hindsight of Champaton factors even before they studied d-branes. Yes?
Is it possible to produce an empty algebra in this way, or just UN?
You can produce any algebra, but it's anything else different from UN requires a little bit something a little bit more sophisticated. So you have to introduce. you discover that there are other objects, in fact, which are called orientifolds. And if you put D branes on top of orientifolds, you get SO groups. If you get anti-orientifolds, you get SP groups. If you now have crazy singularities where you have something that happens to be a very strong coupling at some point, you can actually enhance an SO16 into E8. You can compactify on crazy manifolds, which can also give you a G2 group. Yeah, it turns out that, yeah, as I told you, this theory, all we know is bits and pieces. So there is still, I mean, even though many people have been working on this for a long time, the feeling that I have, at least, is that we still are lacking the full mathematical framework where this thing will fit nicely as a single object. And then this course will be given in a very different way from the one I've been doing it. So far, all we're doing is exploring different regions and discovering different pieces and trying to put them together. That's all we're doing at the moment.
I was going to ask, didn't our original theory only contain closed strings, and now we have open strings as well?
Yeah, that's very interesting. So, indeed, so you'd say type 2A and type 2B, weren't they supposed to be only theories of closed strings? Yeah, they were. But only the fundamental strings were closed strings. Now we discovered that even, luckily, the closed strings were powerful enough to tell us that you were missing something in the theory. And what you were missing was an open string sector attached to these D branes, which are now non-perturbative objects, which you didn't see at the beginning because they are not visible in perturbation theory. But somehow they left a trace in these gauge fields.
So are these new open strings any of the branes that we got that the forms should couple to?
No, this. Oh, you're saying, well, in type 2B you have one branes, right? So these one branes are actually strings. But once again, they are non-perturbative objects from the point of view of the string coupling. And as I said, well, if there was any duality that would exchange the couplings of the theories, maybe those guys, in a very, very strong coupling regime, could become fundamental strings. Okay, so I think this is a good point to stop. Yes?
Does something like that works other than D3 branes?
Yes, so I said I chose D3 because it so happens to be a nice dimension where we could actually live, right? So some people have been building models where the standard model and our point of view, I mean, the universe as we know it, would be given by the D3 branes, actual D3 branes, right? Of course, if you just put the D3 branes in flat space-time, remember, this theory started with how many supercharges in 10 dimensions? 32 supercharges, right? Now, I won't have time to explain it, but the presence of a single one of these objects, as it breaks Lorentz invariance in some directions, it also breaks some supersymmetries. And it breaks precisely half of the supersymmetries. So this theory has 16 supercharges. Do you know any theory in 4 dimensions that has 16 supercharges? N equals 4 superjump. So just the construction I gave you here gives rise to N equals 4 superjump with gauge group UN. Not quite a nice place to live, right? Because the theory is conformal. But it's a first step. So by now there is lots of technology to build models that are very, very close to the standard model. You need really much, much more technology to build something that only has the standard model. And that has also been, I mean, there is a postdoc here. Her name is Natalia Saulina, who has built using more algebraic geometry than I think I want to know. So she's being able, with collaborators, to build models that only have the standard model. So it's really spectacular. But I don't think I'll explain it because, yeah, first I'll have to convince her to explain it to me, and then I could explain it to you. But you can go and ask her. Yeah, she'll be very happy, I think, to to tell you more details about it.